Today's topic is an electric dipole in a uniform external electric field. Pay attention to the word uniform external electric field. So, consider the uniform electric field is rightwards. So, this represents electric field. Consider it is rightward. Now let us consider an electric dipole AB. At A minus Q charge and at B plus Q charge. So the dipole label is AB, and let us consider O, the center of the dipole. As we considered earlier, AB equals 2A, and we know that the dipole moment P is along A to B, and the electric field E, as said earlier, is rightward. Let us consider the angle between them is theta. Okay? So what? Charge plus Q at B experiences a force. How much? Force on plus Q. This is how much? This equal to Q into E. To which side? Along. Force on minus Q equals minus Q into E. This is opposite to the direction of E. So it is very easy to understand that. Therefore, net force on the dipole equals and that equals 0. So very important result. When an electric dipole is placed in a uniform external field, the net force on the dipole is 0. So the conclusion is no translatory motion. We know from the conditions of equilibrium, net force is 0. So no translatory motions are noticed when a dipole is placed in a uniform electric field. Now, let us represent this force in the figure. So this is QE, and this is minus QE. So these two forces are equal and opposite, but they are not along the same line. They are not collinear. And we know that two equal and opposite forces, and if they are non-collinear, then they produce a torque. So a torque is produced. These two equal and opposite two equal and opposite forces and their line of action of forces are different, so they are not acting along the same line, so they produce a torque. Now we shall try to calculate the value of this torque. So what is the value of torque? We know that torque equals, what do we know? Torque equals product of either of the forces multiplied by perpendicular distance between their line of action of force. So these two products you can find, by the way, R cross E also, but we are doing in the simplest way, the easiest way. How can you find the torque? Product of either of the forces. We have two forces, both equal and opposite in magnitude. So take any one of the forces as for this. So torque tau as for either of the forces. Take any one, QE into what? Perpendicular distance between their line of action of force. Line of action of force. If I consider this is, so this is the line of action of force for on minus Q, and this is the line of action of force on plus Q. So the perpendicular distance, draw this. If I consider this AB, if I consider M, so this is perpendicular, then what should we write here? BM. Okay? So QE into BM. Now, if this angle is theta, then this is the angle also theta. What can we write in place of BM? QE, BM equals AB sin theta. Am I right? Let's check this. Sin theta equals BM by AB. So BM equals AB sin theta. Now we are writing this in a very required manner. What is required manner? Check. Q multiplied by AB, the dipole length. So I am writing this Q into AB, then I am writing B sin theta. So Q into AB into E sin theta. Now why do I write Q into AB? Because Q into AB is the dipole moment, and B sin theta, since Q into AB equals P, the dipole moment. Okay? So what is the result? Torque on the dipole. So what is the result? An electric dipole when placed in a uniform external electric field, it experiences a torque whose magnitude is given by PE sin theta. Now the question is, torque is a vector. So what is the direction of this vector? Check. Dear students, here we shall take the result of cross product. Say, anyone can say torque is a vector and PE sin theta can be written as P cross E. In the book we see that. But why? Can you not write EP sin theta? Product is commutative. So PE and EP, there is no difference mathematically. So why PE sin theta is preferred over equal to EP sin theta. If I consider EP sin theta, then I could write E cross P. But why I write only P E sin theta? So I am intended to write P cross E. Check this. Check the diagram again. As dipole center is at O, and dipole we consider that is free to rotate about an axis passing through O, perpendicular to the dipole length. Like here, this is my peg. The peg is the axis of rotation of the dipole AB. So you think about that. If someone is pulling a rod AB along this direction and on at A along this direction, then it will make a turning effect along this. So this will be a rotation. So what will be the direction of rotation? This rotation will be clockwise. Direction of rotation. Direction of rotation, you see, as we see it here, very simple to see that this is clockwise. Direction of rotation is clockwise. Now you check this, come to the conclusion that is, how can you find the direction of this torque? So something is rotating along clockwise, check this, clockwise. So clockwise is the direction of rotation, you check, direction of torque. AB is rotating with center O and about the right plane as axis. So in the clockwise direction, AB is rotating about O as an axis. Then this is the rotation clockwise, check this. Then what is the direction of this torque? My thumb points inward, perpendicular to plane of the board. So I am writing. That is torque is inward. You know, dot and cross. Check. Thumb points inward. If curve of the finger indicates tips of the finger, curve of fingers indicates the rotation. So torque is inward. Now check whether it is P cross E or E cross E. This is the direction of P. Now by the right pen, it is this, or check this as it is shown. This is P and this is E. So this is, if I say P cross E, so my stretched palm along P and I curve towards E through smaller angle between them, then thumb points inward. Had I then selected this at the beginning, stretched palm along E, and then I curl the fingers towards P. Means along AB through smaller angle between them. In that case, thumb would point outwards. Contradiction. But we check that direction of torque as per my sequence, it should be inward. So the direction of torque, the torque can be expressed as though tau equals P E sin theta, we can say that it is P cross E, not E cross P. I am repeating once, E cross P, if it is E, along E, then cross P towards P, and then thumb points outward. So not satisfying this direction. So therefore what can we say? Therefore tau equals P cross, a very useful expression for your topic. Almost in every year questions are asked to the board based on torque. Okay? Next we shall try to see about the equilibriums of the dipole in such a case. let us consider three cases are here. Case 1, theta equals 0, and every time we draw a figure, theta equals 0. What is this? So this is E and this is P. Like you can think about that. Here this is minus Q and here is plus. Okay? So what is the result? As theta equals 0, then so what is the result? Then what will be torque? So torque equals P E sin theta, therefore 0. Torque equals 0. Next. Case 2. Theta is 90 degrees. I shall comment later on. But first see what different cases are available. The first case I consider when the dipole is rotated at an angle theta. The dipole moment makes an angle theta with the electric field. Now if 0, now if 90 degree perpendicular, check this again. This is E and let us consider this is P. So you can think about here something minus Q and here something plus Q charge. So this is the meaning of that. Then what is the result here? In this case, tau equals P. Okay? And the third case. The third case. Third case is very important. Theta is 180. So this is E and this is P. So this is minus Q and this is plus Q. Okay? Then what is tau here? Tau is shed. Sin 180 is again 0. Now the question is the first case and the third case. In both the cases, the torque experienced by the dipole is 0. But in the first case, check this. For the example, let us consider the cap side, the left end is negative and the right end is positive as I checked. So this is aligned, torque 0. Now I am displacing to some extent like this. If this dipole is rotated a bit from its alignment with the direction of E, from this direction, then if I rotate it, then what? And if I leave it, then soon it will after oscillation it will become. Tries to align. Whether in this case it is this. Check this. It is this. So here is minus, here is plus, and dipole move, and this is the electric field. So if I rotate a bit, check this. If I rotate a bit, check this is minus Q. This is E. The minus Q charge experiences a force. Minus Q charge experiences a force opposite to E, and plus Q charge experiences a force along E. So that way, if I disturb it from equilibrium to this state, it will further degrade. Whereas in this case, if I disturb a bit, then it tries to regain the equilibrium. So this is in equilibrium. So the conclusion now I am writing in equilibrium. This is also in equilibrium. Of course, rotational equilibrium. So this is also in equilibrium. But there is a difference from the point of view of equilibrium. But this is stable. This is stable, most stable, and this is most unstable. Most unstable. Okay? And obviously this is unstable. Tau is P. So here the equilibrium is unstable